Okay, awesome. Day two. I realized I pushed it a little bit yesterday. I actually started a week before in this semester, so I'm still going to push it, but I'm not going to keep it at crazy levels. That will be next week. I will build up towards that, but still I will try to push my levels, of course, because officially the semester doesn't start before next Monday. But anyway, we still keep going. Okay, so continue on from electromagnetism. Yesterday we had integration. So I did integral with the mass. We had varying density. Now this time I want to do an example. So let's say that we have now a prism. So we have this figure over here, like this. Goes like this here, and of course it goes here too. I can draw that as well. Goes like this. Perfect. Okay, then we have that this distance here is a, so the distance to the x-axis, the height as well, is a, and also this boundary here is also a. Now, since we have x, y, and z, we can now start labeling this integral. So what I want to do is determine the mass of this object here, right? And I have to do, of course, an integration. So it's a triple integral because this is a volume. And we're given in that example that rho of x, y, and z, rho was equal to rho 0, just a constant, and x divided by a, like that. So the first task, of course, is to get the volume here. The volume is pretty easy. So for the x is just 0 to a, and for the y-axis is x minus a, and for the z-axis is of course a. Yx minus a on the y, so it's of course this guy. This line here is represented as x minus a. Why is that? Because if you draw this guy, you can see, and we have a line here. Let's have a line here, and that's our line. I can draw it a blue because it belongs to our figure. So we have this blue line here. Now, of course, here is a, x and y, and here is also a. So if y is equal to x minus a, if now x is equal to, let's say that x was equal to a, or is it a minus x? Am I a moron? Yeah, because if y equals to 0, it's a minus x. I did a mistake. Yeah, of course it's a minus x. It should be. So if I do a minus x, should that be correct? Yeah, a minus x, yeah. Because now, let's say that if x is equal to 0, let's say that x was 0, then we should get a. That's correct. And of course, if x is equal to a, we should get 0 for y. So that's correct. So I did a little mistake here. It should be a minus x, of course. Not green. A minus x. So that's, of course, the volume. And now we, of course, need to multiply that by a rho. And rho was just, the function for rho was just rho 0. And then x divided by a. The last one was dz. Then we had dy. And then we had dx, right? Okay, calculating on 0a. And then this integral here looked funny. A minus x, and the first integral is pretty easy. Still, this is just a constant, and with 0 we just get a, right? So that just disappears. We get x times, of course, rho 0, like that. And then, of course, we have dy, and then we have dx. Then we can do it here again. There's no y, so just it will be just a minus x. We can do that in our brain, so we just get a times x minus x squared, of course. And I can, just to make this a little more neat, I can do, of course, rho 0 in front, dx like that. And of course, if we now do the integration, this also is pretty easy. I get just rho in front. Remember, I have to put a here. This will get a, this will get to second, so a, I can just, it will be a to the third of both. You can see this will be squared, and this will be, of course, a put in there, so a to the third, right? Because I had one a here earlier, right? Okay, so this is just a to the third is 0. That should be correct. And of course, if I integrate, that's 1/2. And I get that minus, of course, 1/3, like that. And that is, of course, you have 3 6 and 1 3 6 and 2 6. So the answer is, of course, just 1 6 rho 0 a third. That should be correct. I hope so. If I'm a complete moron, that's not correct. So let's hope that I'm not a complete moron then. Okay, good. That was that prism example. That should be correct. Okay. The next concept that we have on our hands are line integral. So what do you mean by a line integral? So let's say I have some curve like this. This curve is labeled C. Now, if I was very thorough, like I'm now, usually I just jump straight to the integral itself, but let's do it a little more thoroughly. So let's say we wanted to look what, let's say I had a particle. I moved that particle alongside this curve here, and I wanted to know how much work is done on that particle. Let's say that this particle lives in a field, for example, a gravitational field. Maybe it's a gravitational field on, I don't know, something else. Because I didn't want a conservative field. Actually, I can say more words about, but it's some field, right? Maybe, yeah. Of course, it's just some vector field, so it could just be the ocean, for example. There's velocities in moving the sea, etc. So that would be a better field because that would be path dependent, right? Gravity isn't path dependent, so it's in some field. So I want to know what would be the work on a particle alongside this curve moves in some field. So let's say I create a vector here, r of I. Now r of I have to ask for a piece that if I moved the particle just a small step, if I just move the particle just a small step, how much work was done on that particle in relation to the field. When you have something moving in relation to something else, that's of course a dot product. So what I mean is that we point to this place here, and then we look at the change in r of I, this vector, and in order to get that particular work there, I get v w of I, which in this case is that field for that particular place. And of course, like I said, we dotted it with the change in r of I like that. And that's a scalar, you can see. That makes sense because of course it's work. Now, of course, the total work itself is just the sum going from I. Now it's nice with physics, no need to write some stupid n, you just you write it so it makes sense. That's what you do. You don't need to be so peculiar about the math. Oh, I love that. Okay, so I just collect all of those pieces because I chop a line. All of those pieces, I get the total work, of course. And if we made those pieces as small as possible, what you would, of course, then have is the line integral, which I'm actually more interested in. So we have the line integral over the curve C. we have, of course, our field, and we multiply that by, of course, it will actually be dr, but in physics we just write dl even though it's the same. dl is more like a geometric interpretation. Instead of thinking about the position from here, we're just thinking about a very small segment here, and that very small segment is just a tangent here and here and here. That's dl, but dr is the same, of course, but we just write it like that because we want that geometric interpretation, even though it's actually sometimes annoying, but maybe it's a good reason, I don't know. we have the formula for volt, also very weird, but yeah, it is what it is. Okay, so that's what we did. And of course, if this was a closed loop, for example, if you circulation is a typical closed loop, so if you have a closed loop, you just do this, nothing more than that. Okay, and of course, if, like I tried to say earlier, if this was a conservative field, the only thing I would care about is, of course, this height, this change in height here. That is what I would care about, of course, because a conservative field is not path independent. So if I had my particle and this was gravity, I would only care about the height here. But if there was something else, if it was path dependent, like I said, if you had something moving through a sea, or if it was friction or anything like that, that would be path dependent, of course. Okay. Yes. Yeah. So now let's do an example. I don't remember what the example is. So let's see. That was the example. Okay. So let's now see if we have something like this, and the curve now is just it's like a unit circle, but half a unit circle. That's our curve. So we have something like this. This is our curve. It's half a unit circle that goes from minus a to a. I usually write it in red, but who cares? So this is our curve C. You know what? I'm going to write this in red. That's just so weird. Okay, a, and then minus a, and this is our curve C. And the field we have, our field, is of course x divided by a in the y hat direction. Okay, so now we want to, of course, calculate this guy. And we have our formula. We have the field, right? And it's in terms of r, so I can just write r there. And then dl, which is a vector, over the curve C. Now, the easiest thing to do, usually in problems like this, is parameterize. Why? You can jump down one dimension. It makes the problem and the integral a lot simpler. So this is a two-dimensional plane, but as you see, a is constant. So we can describe the position vector r just in terms of theta, right? That's just a cosine theta, like that, and a sine theta, like that. Okay, so we have that part. Now we need, of course, now we need dl, right? And we need dl in terms of theta. So I know dl, and dl, like I said, is actually the same as dr, but er isn't a function of theta, so we can just do d theta and d theta. And if we do that, that just is taking the derivative in terms of theta. And theta is not a function of t or something, it's just theta. So this is pretty simple. This is just a, and then we have cosine theta. So this is, of course, just minus a sine theta. And then we have just a cosine theta, like that. Now, in order to make our stuff work, we just move this guy over here, because then I get dr, or in terms of dl, same thing. And I can do that. So this means that what we have here is the same as, and remember, it's half a circle, so it's from 0 to pi. Again, we jumped down one dimension, which is pretty neat, because we don't need two integrals, we just need one. because of the parameterization here. And then we have, of course, we have f in terms of r, which means that we have to plug in a cosine theta, a sine theta. Oh, I'm not going to fit that. I can move this this guy below. That was a little bit too much. Yeah, so I move this guy here. This is r, of course, and now I have to dot it with, of course, dl, and dl is just minus a sine theta and a cosine of theta, and of course we have the theta. So now everything is looking fine and good. Then we have from 0 to pi. Of course, we have to check what it is. So this is our, we put a cosine theta and a sine theta, and what we had for f was x over a. So we only use x. So we have a cosine theta, that's just cosine of theta, but it's just in the y direction. So all of this is just 0 cosine of theta dotted with minus a sine theta and a cosine theta d theta, like that. Now, of course, since this 0, this and this guy goes out. And what we end up with is, of course, the integral of cosine squared theta from 0 to pi d theta. And remember, this guy is the same as 1 plus 2. No, it's 1. Is it plus 2? No, it's cosine of 2 theta divided by 2. That's what it is, yeah. Which means that what we get is, of course, the first one is, we can just leave a there. The first one is going to get integrated just 1/2, and 1/2 is also going to be for both. So I just do a over 2, and then the first one is just pi. And then we have to integrate cosine of 2 theta. That is just plus cosine of 2 theta. Am I a moron? No. It's just sine 2 theta over 2, actually. It's from you set just u is equal to 2 theta. That should be fine. Okay, and of course, if I was a little bit too quick, but if I set in pi there, of course, this guy goes away, and what we end up with is a times pi over 2. That should be correct. Okay, pretty neat. Yeah, now let's go to the next integral, of course, which is the surface integral. Okay, surface integral. So surface integral, I'm not going to do that derivation from scratch. I've done it a bunch of times. But what we can do is think about what it is. The surface integral formula is pretty easy. It's just, we have some field and we dotted it with ds like that, and we do it like that. And this is actually called flux. Now, flux is just, we have some kind of object, and we want to know how much a field is moving through that surface, right? So not the volume, but across the surface, right? So across the boundaries, right? And this integral also, if it's closed, you do that. If it's not, you don't do that. That's just it, right? And this formula is pretty easy to think about. You don't need to do that derivation, at least if you've done it a bunch of times. So I think of it like this. Let's say I had this crazy rain here. So this is my crazy rain vector field for some reason. And I have a bucket here. This was a huge bucket, but who cares? And here is my bucket. And also, to make this a little bit clear, I want to make them a little bit more like that. Yeah. Okay, that's my crazy rain vector field. Yeah. Okay. To the degree that I will catch rain with this top surface here of my bucket, if you just don't think about how big my bucket is or how much rain is pouring down, the only two things that contribute then, like if I want to maximize catching rain, is if the rain is parallel to the normal of my bucket, right? That's the idea. If I want to catch more rain, I have to have the rain vector, right, parallel to the normal of my bucket, right? And the amount of rain I can catch depend on the rain itself then and the size of my bucket. So to do this in calculation, you will say this is the rain, the vector field, right? And I of course just need a position. That's not what I'm trying to state. But then I need to catch the rain. And this, of course, ds is just a small piece of my bucket. But to collect the full size of that bucket, the top of that bucket, I have to, of course, integrate. Then it also depends on how, like I said, how I hold the bucket in terms of the rain. It has to be parallel to, in order to catch the most rain, the rain has to be parallel to the normal of my surface. That will be the best. And of course, I can just write that. So and in order for some vector to be the most similar to another vector, I think of it, of course, as the dot product. So we just dot it, we just do this guy and dot it with the normal there, right? And this is, of course, that normal is just that normal there, right? You could also write this as, of course, S, F, R, and just ds as a vector. That's just these two guys combined, right? Okay, so that's what it means. That's how I think about it. Okay, that should be pretty clear. And this is called, of course, flux, right? Okay, yeah, okay. And this is, of course, as you can see also from the formula, this is a scalar as well. And it's positive if it moves out, and it's negative if it moves in. So if you have a surface and you have flux out, it's positive, and if you have a surface and it's streaming in, it's negative, right? Okay, so now let's see, let's do an example again. Actually, I would do a cylinder, so a bucket is pretty good, but it's actually not that good because I'm not going to care about the flux through the top surface, only around the bucket. Okay, let's do a coordinate system first, so this is a little bit clear. Okay, and then you have my bucket here. Yeah, that was a great drawing. Who cares? Yeah. Then I do something like this. There you go. And this is my cylinder. That's a little bit of a stupid cylinder. What am I doing there? Like, that's a little bit better. Okay, we go with that. Yeah. Then, of course, X, Y, and Z. And now we are going to calculate the surface integral, but only around this cylinder. That's what we want. And of course, I need a field here, and the field is written as F. F is equal to F0, just a constant, divided by A and times actually R, like that. Okay, and we have that I need the radius on the cylinder, that is A, and we also have that the height here is H, like that. Okay, so now, in order to do this, what we need is, of course, that integral. So, and if you remember that integral, we have ds. So what I used to do, you can do this multiple ways. You can actually do this pretty quick with some, I think with Stokes' theorem, you can do this pretty quick. But that's for later. We can do this the more slower way now. So what I would do then is that you have to just describe all of these pieces here. We have the field we need, and we of course need ds. So ds is just a piece on the side, like this. And a piece on the side, if I took this side out from the cylinder, like it just has some bend there, the height is of course just dz, right? And of course, the smallest piece is of course just d theta. But theta is not a distance. So to add to d theta, I of course need a. So I then have a d theta. So dz, the area of the set, no, not dz, you moron. I mean ds is just equal to a d theta and then dz, like that. Okay, and now I want this version here. So not this version. So I want the normal, and normal is pretty easy because the normal here, which is out from the cylinder itself, is always in the same direction as r, right? And r is pretty easy. That we can just I should actually write r first. So r you can just parameterize, right? This can be a function of, right, we can jump from 3 to 2 dimensions because we have a constant a here, and I can just write this at theta and z. So the x value would then be, of course, a cosine theta. The y values, I forget, a sine theta, and the height is just z. So just 2 coordinates like that. And this, of course, n hat will be in the same direction, like I said, but it's a unit vector, so you don't need a. So it just be cosine theta, sine theta, and it of course doesn't have any height. Now we're ready to describe. So let's say that the surface integral, so the flux here, in this case, that looks like a Pokemon. It's just f, and then I want to plug in r, of course. So I have a cosine theta, a sine theta. I have z, like that. I multiply that by n hat, and then I multiply that by ds. So that will be cosine theta, sine theta, 0. This is starting to get long. 0. What was the last one I was looking for here? I have 0. I of course need, I need of course a, and dz is easier, so I will do dz first and then the theta, which means that this is actually 2 integrals, not 1. Whoops. That makes sense. We jumped 1 dimension below. So 2 integral, that was a nice integral. The height is just from 0 to h, and the theta is all around, so 0 to 2 pi, like that. Cool. That's pretty good. Now, the smart thing to do, of course, is to insert for f. What was f again? F was f0 of a, and just multiplied by this guy. So you just get f0 and a disappears. You just get f0. And then, as you see, we get that the last coordinate z just disappears as well. So what we do, we get f0. Then I get f0, and I have a cosine of theta. So you can see that this actually gets pretty neat because I have f0. You can take this a in front. This a disappeared. Then you have cosine of theta, So that's cosine of theta squared. Then we have plus, and then sine squared of theta. And this is extremely neat because goodbye to you. Then we just have dz and the theta. Right. Then this integral from 0 to 2 pi, from 0 to h, is just f0 and a. There's no dz, so we can just actually do the integral it's pretty fast. It's 2 pi h f0 times a, like that. Very good. Okay, that was the flux there. Now the next part is of course differentiation, and this is going to be the last part. Differentiation. The first thing we are starting with is of course the gradient. So what is the gradient? Now I walk a lot in the mountains in the north of Norway, and we use the gradient, not mathematically of course, but we use it a lot. So let's say I had some mountain. And I wish to know what is the sea. Like this could be height curves. So this is a contour plot. Let's say this was 300 meters, 400 meters, 500 meters. So if this was a little bit stupid. So if I walked on one of these paths here, let's say I walked on one of these paths here, for example, if I walked on this guy right here, so if I walked alongside here, like if I'm walking straight forward, I'm not moving, there's no steepness there. In order for me to steepness, I have to go off that track. And the biggest steepness is 90 degrees to that track. And that steepness is what we call the gradient. So it's like, it's very close to the derivative in the one-dimensional case, but this is of course the multi-variable case. So this guy right here, this is what we think as the gradient there. So this is the gradient of f. So the gradient of f is a vector, and that's because of nabla right here. And that's just partial of f in terms of, I also think of it as a total derivative, because it's the partial. We look at how much f changed in terms of x in the x direction, and then how much f changed in terms of y, not 2, in the y direction, and then how much f changed in terms of z and in the z hat direction. That's why this is a vector. And as you see here, we can of course move f outside, and we can actually just write this operator. This is called nabla, or the del operator, which you can see is just partial in terms of x in the x hat direction, partial in terms of y in the y hat direction, and then partial in terms of z in the z hat direction, just like that. Perfect. The next thing, of course, we have now, which makes sense why we usually use this guy, is divergence. So we just looked at flux, and divergence is flux, but it is the local flux, you can think of it. So what I mean by that is, like, if we had some object, again, why are these objects? Physics has like ruined me of writing normal objects. We have always write this stupid blob, but it's alright. So let's say we had this stupid three-dimensional object. Right. If I wanted to know the total flux, right, which is just the flux, it will be the total divergence then. But if I want to know the flux, that will be the whole object. But if I just wanted for one tiny point here, like this, just this tiny volume object, that is the divergence. We're going to look in the later videos, because I'm going to have it at, of course, curl and divergence. This is now curl and circulation is the same thing. So circulation is the global property, right? You can look at a boat that moves circular due to some motion of the sea, or we can place something that spins, and we can see how that spinning object moves like a propeller, I think. Yeah, moves at that point in C. The one which is a point in C is a local property, because it's just at that point. That is curl. And this has the same type of idea. But instead of something that rotates, this is something that spreads out or go in, right? Okay. Yeah. So that is divergence. So we have an intuition formula for this guy. So in the intuition formula, like this, the divergence of f is equal to, you take the limit and we let our change in volume go to 0. So the change in volume there, we have this guy right here, right? That is our small volume object. V is the total guy here. Let our change in volume go to 0. Then what we have is the surface integral, and we integrate. Yeah, I integrate over that volume. That would make sense. So I integrate over that small volume element. Then we do the same thing as we have done. So just f and then ds like that. And then we divide this whole thing on the volume itself. So delta v, like that. I don't know if I think this should be fine actually. Yeah, I can just have the volume element go small. There's no reason to have the delta volume. That's small anyway. I think that's more correct. The idea here is still the same. What we're trying to say is that if you shrink the whole thing as small as possible into that cube, right? The amount of like flux would now be how much flux there were, the amount of diversion will be the total flux and the ratio compared to how big that small piece is, right? And that is divergence. That means we're trying to say is that we have this big flux stream of the surface, and we're just focusing instead of streaming at that point, which is just be at that small volume element, right? Okay, cool. But this is pretty useless when it comes to calculation. So what we do, this is just for understanding. So what we do instead is that we have the nabla, which is, I think, the divergence. Yeah, the divergence of the f of f is, of course, just, what was the divergence formula again? What is it? Is it nabla dotted with f, isn't it? Yeah. Was there an integration there? Oh, was there integration, or is it just nabla? Oh, now I'm actually uncertain. Oh, let's see. Do I need the integration or not? I know it's nabla f. Oh, let's see. And nabla. I don't particularly nice to remember it. I can at least say that here again, if it streams outside of this little cube, it's of course it's positive, and if it goes inside, it's negative. Oh, that's correct. Yeah, I see. It actually is correct. That is the divergence. This is correct. Now, why is this the divergence? Because you can think about what the formula means. Again, if you look at nabla, like I said, nabla was like the total. You have all of those changes. So we have, and this is of course a scalar, because now this time we dotted it. Last time it was an operation on f. Now we dotted it with f, right? So this was partial x in the x direction plus partial y in the y hat direction plus partial z in the z hat direction. Now, why does this formula make sense? If you think about it, this is our infinitesimally small cube. Even though it doesn't look like it, it is. So if I wanted to ask at that point, like this cube will represent this local property. No, this, what I mean, I had flux which was global and this which was local. So this cube represents the local here. And if I wanted to know how much streamed out or in to that cube of our vector field, I of course need to ask the total change in relation, which is scalar product, in terms of that field and then in that direction. So this will be dotted with this guy. So I have to ask how much would something like water stream through this surface? So it's in this direction, right? We're comparing total change of this field alongside, no, not the total change. That was not particularly correct. We are the norm, I think we are comparing the small distance, yeah. So we're comparing the small distance in x, and then the x hat direction is like our normal, and we're comparing that to the field in that same direction. And we have to do it through, of course, all three in order to get that divergence there. That's how I think about the formula. God damn. That's a more rigorous way of thinking about it. I've done the derivations before, so I'm not going to do that again. Okay, good. That's for electromagnetism. Let's do astrophysics. Okay, so astrophysics is just statistics, yeah, which every physicist enjoy. That's the best thing in the world. It's statistics. It's just so fun. I hate statistics. God damn. Okay. So let's see. Gaussian statistics. That's what we're starting with. So Gaussian statistics. And we start actually with just some easy introduction. So P of x. What is P of x? Is the probability distribution. Probability distribution function here. And what does it mean? It means, it means how, if we have some kind of random variable, and we will see how the probability for each of the events, or the numbers that the random variable can take on, what is the probability of that, and we see all the possibilities. That's the probability distribution. It's a lot easier to see through an example. So a typical example could be a coin toss. So let's say my random variable x, a capital X, is equal to that. If we toss a coin, we get 4 heads. That's the random variable. So no, how many? No. The random variable x is how many times we get heads when we do 4 tosses. So no, I could say that, yeah, that's correct. Number of heads in 4 tosses. I think that's how you write tosses. Who cares? That's a random variable. That's a lot better to say. Yeah, okay. So, of course, the probability space, not probability, but the sample space, of course, would then be something like tails, tails, tails. I'm not going to write all. I'm just going to write the first one, and of course the last one, which is just, why did I write 4 dots like that? So heads, 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 which is the last one. But the amount of events is 2 to the 4th, which is 16, right? And we just, let's say, if I asked that the probability that the random variable x takes on the value, which is 4, so 4 heads, that is just 1/16, because that's just one event. So if you did that for all, for 1, for 0, for 2, and 3, then you have the probability distribution. Much easier to understand through that example. Okay, so what does this fun statistics has to do with the construction of a rocket engine? Because that's the main goal of this section. And what it has is that you have that object. What is that object called again? I don't remember the word, but this end object where the thrust will come through, right? And in order to have thrust, that was a very like rocket engine, it was more like that. Yeah. So in order to have thrust, then we have to like throw something behind, right? That's just, or it would make more sense to like do it like this. Yeah. We have to leave something behind, and that's of course just Newton's third law. If I stood on a skateboard and I had a water hose like this, and I turned it on, I will move this way. That's only because I threw the water in this direction. I push some force, and that force gets applied to me, back to me. That's just Newton's third law. And that's how rocket works as well. They have to throw thrust when, like, in order for them to move, they like throw thrust the other way, right? Okay, but thrust isn't just something, it's particles. And those particles have velocities, and those velocities are actually random. And the initial condition of those velocities are random as well, and they follow a Gaussian distribution. So that's why we need statistics. Okay, let's move on. So in order to learn more about Gaussian distributions, we're going to start with an example. So the example here is heights of women. Heights of women actually follow a Gaussian distribution, which is actually just a normal distribution. That's what it means. And then the formula for a normal distribution we use, I'm not going to remember it, so I actually have it written, but I can just say some words on it. It's pure insanity to remember this formula. Okay, especially if you just had like simple statistics. But anyway, it's this guy right here. I can just say some words on it. You have me, and then divided by 2 sigma, and sigma is squared, and we have this guy squared as well. So this function here is actually, this is the function for our normal distribution, and this is the standard deviation here, and this is our mean for a population. So for example, if the average, let's say we had the height of Norwegian women in Norway, and the average was 168, and 168 would go here. And of course, the standard deviation was 6 centimeters, so that would be this guy. Okay, so what does this function represent? It's actually a density function. It's not, because the example I had here, these are discrete random variables, but the random variable of heights in Norway, these are actually continuous. It's not the same. So what do I mean by that? I mean is that you can't ask the probability for a woman being, like, let's say 170, because 170 means 17000000000. You can't get that precision. This will go forever. But what you can't get is ask for the probability between 169 and of course 171, for example. I should actually, just to make my life simpler, I should do this. Okay, so 169 and 171. That's what you can ask the probability for. So since it's a density function, what we have is for the normal distribution to be like this. And the function, of course, in order to get the probability, we have to integrate between those two values. So for example, 169 and 171. Which means, and this is very similar to the mass, that's why it's called the density. In order to get the mass, you have to, of course, take that surface, like, again, you have to take the volume, or in this case, the surface, and then with density, right? And this is the same idea. So actually, the probability, let's say the probability of getting the probability between two heights. So if I wanted to check the probability for women in Norway between 160 and 180, then I would write 160 and 180, and that would be equal to this integral from h1 to h2. And then you would have, of course, that stupid function there, ph, and then dh, like that. So that is what it is. Okay. Yeah. Okay, that is good. What was the next thing I wanted? Yeah, so this plot right here, we can just say some words. If it's normal, the me is here. One standard deviation is about 68%. That is sigma. So 1 sigma from here. That was a nice drawing, but yeah, who cares? That's just sigma from there. And I think the next is 9 97 something. That doesn't matter, right? Okay, so we have that, and we also have something called the full width height maximum. That's another value. I don't understand what it's for because I haven't used it, but the definition is that you go half of the highest height and you ask for the width here. That's the full width height maximum. And we are now actually going to find out why this follows a Gaussian distribution, a normal distribution, but not completely. And here's the reason why. Because let's say that this was something like 140 and this here was something like 2 meters. I write dot, it doesn't matter. If I, for example, if I chose that h1 was 0 and we had infinity and we did that same integral, you of course see that the probability here should be 1. And it should, because 0, you can't have negative heights. And if I go infinite height, of course I cover all the heights. And this is also one of the reasons why this isn't a Gaussian distribution, because usually with Gaussian distribution you do minus infinity. Also, it doesn't make sense to have an infinite height either, because I don't think there's a person above 3 meters. So that wouldn't make sense either. Okay. But that will get, those are so small and will vanish in terms of the tails. So even though we have those two problems, it still follows very closely to a Gaussian distribution, right? Okay, so that's just a little bit of a Gaussian distribution. You can do some calculation with this. If, for example, I can do this on the calculator, I actually should do. I think the task is that I want to use us to use numerical integration, but I haven't used any time on that. So let's try it with the calculator. So let's see. I had this calculator earlier. What is it? TI 84 plus online. Yeah, that one works. Start TI 84. Here we go. Okay. So what we need is second, and we need a distribution. And remember, it's the normal, but it's the normal CDF, like that. Now the lower, again, we want the question I had in my sheet was that we wanted to know out of 2 million women, how many are above 190. So the lower bound will then, of course, be, I can't write numbers, do I have to write here? Okay, 190. The upper bound is, of course, just infinity, so just could do 10. You could do 10, and you can do that to the power of, I don't know, 20, something crazy. And then we have been given that that is just, the average is 168, and the standard deviation is, of course, just 6. Then I get that probability there. That's the probability. And if I took that probability and I multiplied that by the amount, they said it was 2 million. I don't know, it's 2 million women in Norway. I think it's more. Maybe this is old. I don't know. So that's just 2. Oh, I can't write there. So it's 2 multiplied by 10 to the 6th, of course. Okay, and that's 246 if we average up, right? That's correct as well. Cool. Some good calculator training. That works as well. Okay. Yeah. Now we can do the last thing here, which is part 2, and that is redefining the mean and standard deviation. Why do that? Because usually we don't have the population. So now we use the sample value. So if we had a sample value where n is equal to 1,000, so let's say 1,000 women, for example. From our sample value, we can of course calculate the mean. So usually we have n is equal to 1,000, and we label it that one women is x of I, and I, of course, is for, oh, it can just be like that, x of I. And then, of course, the sample mean. So if we take mean, we write this notation for the mean, and that is just 1 over n, of course, 1 over n. Then it's the sum of x of I and then I to n, like that. That should, of course, be correct, like that. Okay, so that's the easy part. There's also one detail here, and that is that n should actually, and this will come in the standard deviation too, I think, but n should actually be n minus 1. And why is that? Because when we have, let's say, the average, oh, I think that should apply to the next one. We'll see. But anyway, for the standard, I think maybe just for standard deviation, because we get another number there. Yeah, but I can just say some words on it. When you do typical sampling, you have to be careful of your sample, because often you get another number. That's why I think from standard deviation, because in the standard deviation we get the mean, so we have another number. That actually means that we have n plus 1 values, not n values. That means that we have more information, but we haven't gathered more information. We just calculated the mean then. So that doesn't make sense then, so usually you do n minus 1. But in astrophysics we have such crazy large values, so there's no need, we can just use n. So thank God for that, less calculations. Okay, but this, I think, yeah, this, I don't think this makes sense for the mean, it's just for standard deviation, because then you have the mean inside there. Here, there's no extra values here, so I don't need n minus 1, of course. Yeah. So now look at the standard deviation, which needs the mean. So if you start with, if you actually want to get the deviation, standard deviation, of course, is just how much we are moving away from the mean, of course. So if I just wanted the deviation, like how much I'm from the average, that's just 1 point minus the average, of course, right? But again, I want the average of that too as well, because this isn't enough. I just don't want 1 point, I want from all of them. So I want from the average and from all of them, but this will actually cancel out, because we will get minus on one side and plus on one side, and we can end up with 0. But actually standard deviation is how long we are, so the length from the average, right? So the length from the mean, which means that we should square this guy. So this is the length of x minus x like that and like that squared. That is what it is. Okay, perfect. Now we can calculate this guy. This guy isn't that complicated. So it's just x squared, and we can apply, remember that these brackets, square brackets here, they actually represent what we have here. I can do it just to notify this is actually this, as you see. And that's nice about sum, you can just move things around. With sum, you can treat often like a constant, very often. So we can just move things around. So we can move this x squared to like this. Then we have in the middle, we would have minus 2. Then I would have x. Then I would have x like that. And then I would have plus. And then I would have x, but the whole thing squared. So the mean squared then. Okay? And this is pretty neat, because I can do x squared like that, and I can do minus 2. Again, it's sum, you can move things around. So this is the same as x plus x squared. And of course, and we had 2 here as well, but doing the operation twice doesn't make any sense. So you can just remove those away. And then you have 2 minus, this will be the same, because I have minus 2 and multiply. So I have like this squared plus this squared. And then I have x, but this guy individually squared. And what I end up with is, of course, just x squared like that. And of course, minus, because I have 2, and the whole thing squared. And if you just replace those square brackets, like I said, they represent 1 over n, and I have I, and then of course x of I, just that piece squared minus parentheses 1 over n, the sum like that, x over I, but now we have the whole thing squared, and that's the final formula. Pretty neat. Okay. Yes, now we are starting to get finished here. We can also get the mean from what is called the first moment. So I'm not going to derive the moment function. I'll see if I do, if I need it, but from the first moment, and that will be just if we did, like again, from 0 to, of course, infinity, and then let's see, that will be just, of course, yeah, then I would just have, is it, I think it's, yeah, just x, and then p of x, the p of h, of course, because we did h, and then the h, and I should, of course, remove x there, so just h. Okay, so what does this represent and why? So here, instead, the moment generating function is that instead of finding the mean like we did, what we're doing here now is that we are weighting each value. So I look at some height, and then I weight it with how likely that value is. That's another way. And if I, of course, add all of the possible heights with how likely they are, of course, it will collect up to the mean, right? Because I have from 0 to infinity here. So that's just what you're doing is you're just checking, okay, I have some value, then I ask, and then I just weight that value with how probable it is. So this is from the first moment, from the moment generating function. Okay. You could also do the second moment. If you do the second moment, what you will get, of course, is the standard deviation, and I don't need to write that. And the last thing I just want to say is that this guy can also be replaced with a function that also works as well. So if this was some kind of function like BMI, we could actually calculate the probability for, let's say, I don't know, women to have a certain BMI. That was the example. I don't know what's, I think that was because we could replace that guy with a function. Let's say we had f of h, for example, and then h was equal to, I think it was m over h squared. Then we can use that as well to get the probability for a certain BMI, but yeah, we don't need that. That's enough for me. Okay, perfect. That's good. I'm happy, and see you tomorrow.